Okay, unless we forget, when it comes to technology and engineering, somebody has to go into a lab and actually build things and use the theory we've been developing. And it's a great pleasure to Professor Akira Furusawa, who's not only developed a lot of experimentation here, but has actually implemented many of the ideas we've been thinking about in quantum technology and related to quantum control. So it's a great pleasure that he's agreed to come here and tell us a little bit about current developments.
First of all, I'd like to thank John for giving me the chance to be here. The title of my talk is Realization of Squeezing of Single Photon, Squeezing of Single Photons and Dynamic Squeezing Gate. And the subtitle is Linear and Nonlinear Feed Forward. I'm pretty much experimentalist, so totally different word from yours. These are my collaborators. This is my group at the University of Tokyo and some visitors from especially UK. And also I have many senior collaborators. And today, particularly this Radim Philip and Radamista and Petr Marek. Let me begin with this famous Carl Cave's paper on gravitational wave detector. This is gravitational wave detector by using Michelson interferometer. And if we put squeezed light from here, we can get better resolution beyond the classical limit. It is very famous. And the essence here is that quantum noise reduction with squeezed light. This is pretty much subject today. And also, this is my experiment for teleportation in 1998 at Caltech. This is some input state is teleported here. In that particular experiment, we used a coherent state as an input. But nowadays, we can teleport a qubit by using this setup. Here also, we are putting squeezed vacuum here, or making entanglement by using this beam splitter, and put here and here. And in that sense, this is again quantum noise reduction with squeezed light. And also, here we are making homodynamic measurement here and making feed forward. So this is linear feed forward, application of linear feed forward. I'll talk about this and other things later. So the topic of today is quantum noise reduction with non-classical state of light, and also linear and nonlinear feed forward. My final goal would be realization of universal quantum information processing. By using Seth Lloyd and Brownstein's paper, we can make universal quantum information processing by using these operations. One is linear or Gaussian operations. Those are phase space displacement, and phase space squeezing, and phase space rotation. Those are all linear or Gaussian operations. And for universal quantum information processing, we have to have one more. That is nonlinear or non-Gaussian operation. For our case, that is cubic phase state, making this Hamiltonian, this unitary operation. Hamiltonian is here. And also, today I will talk about for realization of everything by using quantum noise reduction with non-classical state of light. And also, for this Gaussian operation, we realize them with linear feed-forward. And for this nonlinear or non-Gaussian operation, we use nonlinear feed-forward. And now I'd like to start with this squeezing. I'll talk about squeezing of single photons and shredding a cat states. And again, it is application of linear feed-forward, and it is for a non-Gaussian state input. In shredding a picture, it is called gate teleportation because this ancilla squeeze vacuum and this squeezing operation is teleported to this input, and this is the output. Teleportation operation is teleported here. So the point is that we can use arbitrary input state, and this squeezing operation or squeeze vacuum is always just squeeze vacuum. So it is called universal squeezer. In Heisenberg picture, it is very easy. This is input state, and this is ancilla squeeze vacuum. And here we make homodyne measurement in P quadrature and making feed forward. And we make displacement operation here. And here we are doing linear feed forward. Operation is like this. This is measurement value. This is input-output relationship of this operation. If we take average, this part disappears because this is ancilla squeeze vacuum. So this averaging becomes 0. So we can neglect this part. So it is pretty much squeezing operation. And also, even without averaging, and if we have enough amount of squeezing here, we can neglect this part like this. So again, it is squeezing operation. And also, we can tune the squeezing level, just changing this transmissivity. And we don't have to do nonlinear operation, just making linear feed forward for changing squeezing value. We realized that experiment like this. In this particular experiment, input state was single photon or shredding a cat state. In the case of single photon, here, first of all, we make parametric down conversion. So this photon divided into 2 photons, red and orange. And here, orange, this cavity is resonant to orange photon, so just pass through. And this red photon is totally reflected. And if we have a click here, I mean, we detect orange photon here. We have a single photon here, single photon of red photon here. And here is our squeezer. This is ancilla squeeze vacuum here, and this is beam splitter. and we make homodynamic measurement in P quadrature and feed forward. And we have limited bandwidth here, so we have to compensate this time delay by using optical delay line. And then we make a displacement operation, and then we have output and verify the output. And in the case of Schrödinger cat state input, we make photon subtraction. In this case, this is non-degenerate OPO, or parametric down conversion, but here we are making squeeze vacuum. Squeeze vacuum is a superposition of even photons. And if we have a small portion here and we have a click here, we can subtract single photon. So this superposition of even photon can be converted into superposition of odd photons. That is our cat state. In other words, it is deterministic elimination of vacuum component. That's why we can eliminate this part. And we can make a superposition of two waves, like this. And we squeezed these two states. So this is a sort of gate teleportation picture, but it doesn't matter at all. And this is our single photon state. It is not simulation. This is experimental data. And this is marginal temporal distribution of amplitude. So only two waves, which means this is energy eigenstate. So we cannot determine phases. That's why this should be some amplitude, but we don't have any phase. So two lines. And this is photon number distribution. And this is 1. And the purity of this single photon is more than 80%. And we can get big negativity of Wigner function. And this is our ancillary squeeze vacuum. And by using these two and combine here by a beam splitter and homodynamic measurement and feed forward, and this is one of the output at some value of t. We can see negativity of Wigner function, and we can clearly see a phase dependence. And that is superposition of two waves at cat state. And we change the transmissivity and change the squeezing value like this. So we can change the squeezing level like this. And also, we squeeze a cat state. Squeezing a cat is a bad wording, but we squeeze a cat state. This is our cat state, and again, this is ancillary squeeze vacuum, and made a squeezing operation, and this is the output. Now there is almost no phase dependence, so it is pretty much, so it is a little bit squeezed, but in my original picture, it is pretty much circle, so almost no phase dependence. So we succeeded in making a single photon by squeezing of a cat state. Now I'd like to move on to another topic, that is quantum non-demolition interaction. That quantum non-demolition interaction unitary transformation is like this. And in Heisenberg picture, that is like this. So this x1 is always x1. but this information appeared here. So, and this is called QND gain, G. And if you just want to make a QND measurement, these two equations are enough. But we want to make QND interaction. So in that case, we have to have another two equations or input-output relationship. And in that case, P2 is always P2, and this information appeared here. So it is kind of mirror symmetry. And if we go to Schrödinger picture, it is like this. And here we set G equals 1. That is because this is continuous variable version of CNOT gate, entangling gate. And this operation can be realized by using two squeezers and two beam splitters. And we did that experiment. Again, these are two universal squeezers, ancillary squeeze vacuum and homodynamic measurement and feed forward. And here again, ancillary squeeze vacuum and measurement and feed forward. Two squeezers and two beam splitters. And this is input-output relationship. It looks very messy, but if we have enough amount of squeezing, this part vanishes. That is quantum noise reduction by the squeeze vacuum. And this part can be regarded as QND gain. And we can tune this QND gain by just changing this T, transmissivity of T of these two. And in our experiment, we set that is equal to 1. Actually, we changed to 1.5, but it is pretty much the same. And this is the result. So this experiment was a very preliminary experiment. So the input was just vacuum. So two vacua are coming into our QND interaction gate, and we had some output. So before QND interaction, both X1 and X2 were short noise level, at short noise level. That was because both were squeeze vacua. And after QND interaction, X1 should be X1 should be X1. But of course, we have some extra noise, but that is small. So that was less than 1 dB. So it is pretty much okay. And in the case of X2, both are squeeze vacuum. So after the QND interaction, it should become 3 dB up, 2 times bigger compared to this short noise level, and it is about 3 dB. So we can check this input-output relationship, and also we checked another part, this one. And again, P2 is a little bit bigger, but not much, and this is 3 dB up. So it is pretty much QND interaction. And of course, inputs are vacuum, not so interesting. So now we are trying to make a QND interaction for single photon. Again, this is non-degenerate OPO, parametric down conversion, and we are making a thin photon here. And we two squeezes, universal squeezes, and doing QND. So now I'd like to move on to another topic, that is dynamic squeezing gate. That is for realization of nonlinear quantum gates. And subtitle is nonlinear feed-forward. Again, for universal quantum information processing, we have to have all Gaussian operations and only one non-Gaussian operation. And again, for that purpose, we can use quantum noise reduction with non-classical state of light. And for Gaussian operation or linear operation, we can use linear feed-forward. But for this non-Gaussian operation, we have to make so cubic phase gate, we have to make nonlinear feed-forward. I'll talk about this nonlinear feed-forward now. This is cubic phase gate. This is x cube. And showing a picture, this is like this, of course. And in Heisenberg picture, I love Heisenberg picture. X is always x, and p is like this, x squared here. So this is minimum nonlinear operation. So if we can make this cubic phase gate, we can calculate multiplication. If we can only make Gaussian operation, which means we can just make summation. So by using this one, we can make multiplication like this. But unfortunately, we don't have good nonlinear crystal for this cubic phase gate. So our strategy is state preparation with strong light, and then make a gate teleportation. Actually, it was proposed by Gottesman, Kitaev, and Preskel in 2001. In shading a picture, this is input, and of course, this is gate teleportation. This cubic phase gate operation is teleported here. And so first of all, input state, arbitrary input state is entangled by using this QND gate and make measurement here. This is a homodynamic measurement and feed forward and make this correction or nonlinear feed forward. Because this Q appears like this. So it is pretty much nonlinear feed forward. In Heisenberg picture, this is ancilla state, but this is Heisenberg picture of cubic phase state, ancilla state. And the input-output relationship, again, like this. Square appeared here. And of course, nonlinear feed forward. For the ancilla of cubic phase gate, we have to prepare a cubic phase state. And in showing a picture, this is like cubic phase state is like this. And Heisenberg picture is like this. It is a parabolic function in phase space. And if we If we use for this one a squeeze vacuum, and the squeezing level is finite, the cubic phase state becomes like this. So parabolic function, and the squeeze vacuum is like this. And we can approximate that state by using superposition of 0 and 1 like this. Of course, it is a little bit different, but the essence is very similar. So this structure and this negativity. A little bit displacement here, but we can compensate by using linear feed forward. It's easy. And we succeeded in making that superposition of 0 and 1 like this. So we can prepare the ancilla state now. So now we have to make nonlinear feed forward. For that purpose, with Petromarek and Radin Philip, we thought about experimental realization. But even for us, it was too difficult, too complicated. Yes?
What sort of non-linearities you think you can obtain with this kind of ancilla states?
Yeah, I'll talk that one later. That is very, very important point. But now we found the very easy way to realize that cubic phase gate. I think that is the simplest case for the realization of cubic phase gate. If it is possible, please prove this. This is the simplest. I'm not a theorist, so it looks like very simple, simplest, but I don't know. The point is that just ancilla cubic phase state and squeeze vacuum, but it is pretty much a nonlinear feed forward. So nonlinear feed forward is very complicated, but it is just classical nonlinearity. And this is input-output relationship. And if this ancilla squeeze vacuum is has enough amount of squeezing, these parts vanishes. And if we have very good ancilla state of this cubic phase state, this part vanishes. That means this input-output relationship becomes 3 dB of squeezing and cubic phase gate.
This we split is balanced? Or?
No. Sorry. This is balanced. These two are balanced. Sorry. And again, these noise reduction. This is quantum noise reduction with non-classical state of light. But in another word, the nonlinearity or non-Gaussianity comes from nonlinear feed forward. That is just classical. And of course, non-classicality comes from this non-classical state. negativity of Wigner function comes from, of course, from here, not from feed forward. So this is, I think, a very important statement. We cannot make non-classicality even with nonlinear feed forward. We can only create non-classicality by using non-classical state of light. So now we are trying to realize this experimental setup. Of course, it looks difficult. So the point is that first, here we make homodynamic measurement, measurement x quadrature, and calculate this arc tangent. This is gain of cubic phase gate. So it is given, gamma is given. So by using this measurement result, we calculate this one. And this theta is calculated, and then we make homodynamic measurement again, but depending on this theta. So depending on this measurement result. Again, this is homodynamic measurement. And we make displacement operation, but the gain is depending on this theta. So it is pretty much complicated classical circuit. But non-classicality is very simple. So in some sense, this non-classical quantum optics part is not so difficult for us. But this non-linear circuit is very difficult for us. So in some sense, it is doing circuit QED. And now we are making that classical circuit. So simplified like this, and we put some, we have a function generator, and we changing this copper, and we calculate this arc tangent here and get this value. And by using this value, we change the measurement basis here. And making displacement in phase space by using this gain. All depending on this copper. Yeah.
So can I ask you, what is the main difficulty? Can this measurement and so be just programmable and you feed it some values? It's a matter of the time it takes to calculate. What is difficult about?
So, of course, if let's see, if this is very slow process, in that case, this feed forward takes time. Again, this feed forward takes time. So this is kind of entanglement. So if we have a time, we have time here. We have to have very long time delay, optical time delay. So it makes the system very fragile. So even for a universal squeezer, we used 12 meters. So this system has finite bandwidth, which means time delay. To compensate that time delay here, we have to very long optical delay. And in reality, if we have use slow circuit, let's see, a moment. Yeah, here. So it takes time. So we have very long line here, and again we have very long line here. So it's unfeasible. To tell the truth, even for 100 meters of delay, in principle it would be possible, but in reality, we have phase fluctuation and so on. It is very hard. So that's why we have to, our calculation should be very fast. And here, and we are modifying the circuit. And that's why we are making the circuit with analog circuit, not digital. Digital is too slow. And this is input-output relationship of this gate. This is input, and this is ancillary squeeze vacuum, and make measurement depending on this signal. And of course, this is depending on this signal. And this is the input-output relationship. And again, if we have enough amount of squeezing, this part vanishes. So this is sort of squeezing again. And if kappa less than 0, it becomes like this, and kappa equals 0, like this, and kappa bigger than larger than 0, it should be like this. So, and this kappa is time dependent. So we should dynamically change this squeezing. So that's why we call it as a dynamic squeezing gate. This is nonlinear feed forward. And in our particular experiment, we put this omega equals 1 megahertz. And for this input, our input is also time dependent. It oscillates like this, oscillating coherent state. Sometimes 0, and sometimes here, and sometimes here. And this is sinusoidal sine curve. And in that case, the output should be like this. So kappa equals 0, around 0, so it should be like this. And kappa less than 0 is like this, and so on. And we check that one. And for that purpose, first we try to make that nonlinear feed forward with digital circuit, but it was too slow. We had a big latency problem. So in that case, we had to have a 15-meter delay. And this is at here we have to calculate arctangent kappa. And for that purpose, we made this circuit. And this clamp circuit is like this. So by using this circuit, and arc tangent should be like this. It is a little bit weak, but our experimental result was like this. So pretty much arc tangent up to 10 megahertz. And also we have to make this one, a nonlinear amplifier. And this is our nonlinear amplifier. Output should be like this. And this is our result. So pretty much this circuit. And then we checked the performance of this one, dynamic squeezing gate. Here, this is this input. Copper is changing like this, 1 megahertz. And here, this is input state. This is temporal dependence of this average value of x in. So, and P quadrature was always 0. X was like this. It was 5 megahertz. And this is the output. So it should be like this. And point is that if copper is bigger than 0, X and P should be in phase, because P equals always 0. And one moment, I should a little bit back. X out should be half of power. So this X becomes half of power. And P in, average value of P in is always 0. And copper changes like this. So, and we have some coefficient like this. And in the case of copper is bigger than 0, here, these are in phase. And that is because this part is plus, positive. But in the case of copper is less than 0, and the sign is minus, X and P are opposite phase. That is because this one is negative. And we checked variances at X quadrature, and the X quadrature was always this level, less than this short noise level, because X in and X in should be 3 dB squeeze. Of course, we have extra term, so not 3 dB, but less than short noise level. And checked 45 degrees and P quadrature. And here we have the maximum of variance. And here, this 0, minimum of variance. It is pretty much like this. And by using these values, we calculated the squeezing level and squeezing angle. And squeezing angle, that is the angle from this P So it changed like this. And also squeezing level, anti-squeezing level is dynamically changing like this. And the squeezing level is also dynamically changing like this. So it works very well. Now we are trying to do this experiment. But we have the last problem, that is we have to determine this value. That is because our experiment is not pulse light experiment. We are using a cavity. So in that case, our ancillary state and everything has some wave packet. In that case, to determine this value, we have to make calculation like this. It takes time again. But we found a solution. That is, if we can make this wave packet, this integration can be realized just by using this integration low-pass filter. So now we are trying to make this wave packet. The reason why we have this wave packet is that red and orange photon, both photons are resonant to this cavity. Sometimes, so of course, these two photons, red and orange photons, are simultaneously created. But the timing from getting out of the cavity is different. So in the case of orange photon is coming out fast. In that case, we make this part. And if a red photon is getting out fast, in that case, we make this. So to make change the situation, only orange photon are resonant to the OPO cavity. In that case, orange photon, red photon is totally non-resonant to this cavity, so always fast. So we can make this wave packet. Now we have all solutions. And now we will have a cubic phase state. And again, we are doing this crazy experiment. But it is kind of maximum. So we cannot expand this experimental setup. So now our solution is making a chip. So this is our teleportation chip. It was made by NTT. These tiny parts are all Mach center interferometers. And as you know, Mach center interferometer can be used as a beam splitters. And we can change the transmissivity or branching ratio by using changing the temperature of one path. So this is, at the moment, it is just for passive optics. But now we are trying to integrate all nonlinear components here. So in the near future, we can make cubic phase gate chip. And we make integrate a lot of them. Thank you for attention.
In your chip, I was wondering, what is the phase stability of the Mach-Zehnder interferometers? Do you have any on your chip? Can you tune it, or do you have any fixed?
So
How good are
if we stabilize the temperature, phase stability is almost perfect. So it depends on the temperature.
So I'm very curious as to why you didn't think of or didn't do a post-selection test. So you have this beautiful 0+1 state to be able to create.
Mm-hmm.
You have the rest of the apparatus.
Mm-hmm.
Nonlinear processing has been a bit of a challenge, and I appreciate that. But I'm sort of curious. You could also do a post-selection based approach, which is a step along the way.
Mm-hmm.
So what prevented that, or alternatively, why was it not interesting to you?
It's interesting. Of course, as a first step, we will try to do post-selection and then go to deterministic.
I see. So in other words, you might first start with just fixed data, hope that you get something that's close to that data.
Yeah,
and
yeah,
if you did,
yeah,
then
yeah. And also, the final step should be make optical memory, quantum memory. We also have that solution. So to make deterministic, we have to store this one. This is very easy, but we have to store this one. And for that purpose, we have to have optical memory or quantum memory. And we have that solution.
Is there any reason you can't use this squeezed cap for an on-demand source then?
Oh yeah, of course. That would be our first trial. And then, of course, this is just a superposition of 0 and 1. So in that sense, it is easy. But if you make more precise cubic phase state, that should be more photons and very complicated superpositions. And also, we are thinking about using photon number resolving detector with superconducting materials.
Yeah, it's probably a naive question, but what I was wondering is if you build a cavity into your setup and you have the light going, your feedback loop around the cavity, then your output light might experience like several feedback pulses, not only one.
Yes.
Would that be a way of increasing your nonlinearity?
Actually, we have some experience on that for squeeze vacuum. So first, we create a squeeze vacuum by using OPL, and then that was coherent feedback. So this output was coming back to this original OPL, and then enhanced the squeezing level. But again, we have a problem because for this feedback, we have to have some time. It takes time. That means the system becomes very slow. In the sense of, for example, squeezing, that is bandwidth of squeezing. So if you use coherent feedback or even classical feedback, you have to think about the bandwidth of the system. If you make a feedback, the system becomes very slow. That is also true for cavity QED. But we have to make a very fast processing. So even for quantum computation, cavity QED is, in my opinion, it is too slow. In our case, our clock time at the moment is 100 megahertz. not 1 gigahertz, but 100 megahertz. That is determined by this homodyne receiver, and also squeezer bandwidth. Our clock time is determined by this ancillary squeeze state and also this homodyne measurement. In the case of cavity QED or even feedback system, in that case, this bandwidth is very narrow. It means very slow process. Of course, it is not good for processing, but very good for error correction. So you can stabilize some systems. That is very important for error correction. So you have to think two ways. For processing, the processing should be very fast. But for error correction, the system should be very robust. That means response should be very slow.
Just one quick question. I was going to say, is that timescale issue or bandwidth issue changed if you work on a chip instead of on an optical cable?
Yeah, of course. That is another reason for we are using optical chip. Especially at the moment, squeezing bandwidth is determined by the cavity bandwidth. But if we can use a waveguide OPO or even OPA, optical parametric amplifier, the bandwidth becomes like 1 terahertz or so. That is because it is just determined by phase matching temperature. Phase matching condition. So that is more than 1 terahertz, 10 terahertz or so. So in that case, the limiting factor would be homodyne detection. So that's why we broaden the bandwidth this homodyne detection up to 1 gigahertz, because nowadays computers' clock time is several gigahertz. That is a limit.
Well, no further questions.